Good day everyone. Before we start the video, we would like to acknowledge our dear instructor of structural theory, Engineer John Mark S. Tambong. Without his presence, this video will not be possible because he is the one who provided us the task to make a video on these four topics. So thank you sir for the opportunity that you have given to us and may God bless us. Proceeding to group members. And this is the group of Cuartero, Duran, Horserada, and Magpayo. We will discuss the four topics, namely the moment distribution method, three-moment equation, analysis of determinate frames using portal method, and lastly, the analysis of indeterminate frames using cantilever method. We will discuss the principles of these topics and provide two problem-solving sessions on each topic. The first topic to be discussed by yours truly will be the moment distribution method. It was developed by Hardy-Cross in 1924. Was the most widely used method for analysis of structures from 1930. So before the existence of computer softwares, there is already a method for analyzing structural buildings. This method is also known as the stiffness method. In order to apply the method of moment distribution, the student must have a complete knowledge of the fixed end moments of the different types of loadings. The figures of the type of loadings and its specific formula will be provided below. Before we proceed in solving a problem, let us have a knowledge first about the steps in this method. The first step is to understand the figure and label all the joints and loadings. The second step is to analyze what kind of loadings are acted upon the members. The third step is to lock all the joints that are not fixed. Examples are hinge and roller supports. The fourth step is to solve for the distribution factor with the formula of member of stiffness over the summation of all the member stiffness. Member stiffness K is denoted by the formula for EI over L. This is TF, it means distribution factor, and it is equal to the, again, member stiffness over the summation of member stiffness, wherein K is also equal to 4 EI over L, wherein EI is the flexural rigidity and L is the length of the member. E is the modulus of elasticity and I is the moment inertia. In the problems we will be solving, let us just suppose E or I or both of them to be constant. The fifth step is to solve for the fixed end moments using the specific formula for the type of loading in a member. The sixth step is to apply a balancing moment, distribute the balancing moment, carry over 50% of the distributed moment and repeat. And repeat the process until the values are almost balanced or near zero. So we also have an optional step. So it depends on your problem. If your instructor or lecturer asks you to draw the diagram, so in this method you can also draw the diagrams, the shear force diagram and the moment diagram. So here are the figures that has the specific formula depending on where is the loading is located and what type of loading. So here we have a point load at the center. So if this is a roller support, we will make it a fixed end. So all of the edge of this beam should be fixed. It will be locked and considered to be fixed, even though it is a roller or a hinge, etc. So in this figure, we have P as load, L for the length, and P is located L over 2 from, let's say this is A and this is B, so L over 2 away from point A and L over 2 away from point B. So it is basically in the middle of the beam. So our moment equation or moment formula for this will be PL over 8 in this type of figure. So in this type of figure, we have WL squared over 20 and here WL squared over 30, since this is a triangular type of loading. So we also have a uniformly distributed loading, so it is equal to the formula of WL squared over 12, wherein L is the length and the W is the uniformly distributed load. So we also have a settlement here, type of beam, that we can also solve for. Here, if the point load is not at the center, it is denoted for the formula of PAB squared over L squared, and if the B is longer than A, we have PA squared times B over L squared. Here we have a triangular type of load wherein the highest load is in the center or at the middle of the beam. So the formula for it is 5 WL squared over 96, and also the other side 5 WL squared over 96. So we can proceed now in solving a problem. So for this problem we have here, it is asking for the reaction forces. So we have a beam with a total span of 20 feet, a load from point A, from fixed point A, 80 kilopounds, 5 feet away from A, and 40 kilopound, 5 feet away from the roller support B, and we also have an I here, and 1.5 I in the member AB, and I for the member BC, and lastly another roller support at point C. So actually guys, it depends on you whether what do you want to solve first. For me, my go-to is to solve first for the distribution factor, but you can also solve for the fixed and moment first, then distribution factor. So it depends on you whether what do you want to solve first or not. So once again, our distribution factor is denoted with the formula member stiffness over the summation of member stiffness, where member stiffness is equal to 4EI over L. So let us solve first for DFBA. DFAB. So I almost forgot. If our point is fixed, it should be equal to 0. While if it is hinge or roller, the distribution factor will always be 1. Okay, so we need to note this principle. So if the point is fixed like this in A, we have a fixed point here, the distribution factor will always be 0. While if it is hinge or roller, it will always be equal to 1. So let us proceed in solving the problems. So we have DFAB equals 0, DFCB equal to 1. So let us solve for DFBA. DFBA So dFBA is equals to the member stiffness BA over the summation of all the member stiffness. So we have KBA and KBC as our member stiffness because the point B is connected to point C and point A. That's why it has a stiffness. So let's substitute the values. So KBA is equal to 0.6 over 0.6 plus 0.4, and it will equals to 0.6. So how did we get the 0.6 and 0.4? So here it is. As I have explained earlier, the formula for the member stiffness is 4EI over L. As you can see here, 4EI over L. So we will just substitute the value in this formula. So we have our member BA to be 10 feet, 5 feet plus 5 feet, 10 feet, and our moment inertia 1.5i. We'll just basically put it there, close and open parentheses, and E is constant in this problem. E is constant in this problem, guys. So after solving, we got this 0.6. Now solving for the member BC, member stiffness BC, this member, it is still 4EI over L. Okay, this 4EI over L. So basically, just substitute the values. 5 feet plus 5 feet, 10 feet. This is 10 feet. 4EI over 10 feet. So we also have an I, but we doesn't have a number beside it, so we'll just put it in there, I. E is still constant, so 4AI over 10. So solving for that formula, we got member stiffness BC 0.4. Let us erase this first. So for our distribution factor at BC, it is equals to member stiffness BC over member stiffness BA plus member stiffness BC, or the summation of all the member stiffness in the beam. So member stiffness BC is equals to 0.4, member stiffness BA is 0.6, and again BC 0.4. 0.4 divided by 0.6 plus 0.4 equals 0.4. To check if we really got a 1 in the distribution factor in B, we will add these two, 0.4 and 0.6, and obviously it is equal to 1, and we are correct. Let us now proceed in solving the fixed end moment. So, before I forgot, our sign convention for this problem will be counterclockwise. Counterclockwise is positive, while clockwise is negative. As you can see here, it's negative. So this will be the formula we will be using, PL over 8, wherein this is L, and we have L over 2 here, L over 2. So let us check if we put the right formula here. Here. We got it right. So basically, this was 80 kilopound, then 5 feet, and 5 feet also. So we will be using this formula, PL over 8. So let us solve first for the fixed end moment at AB. So fixed end moment at AB. So fixed end moment AB equals to PL over 8. Then substitute the values. 80. This is 80 times 10 over 8. So why it is 80? Because it is the point load, this one 80 plus the length of the member, which is 10 feet. 5 feet. 5 feet plus 5 feet. So it will equal to positive 100 kilopound feet. So our fixed end moment BA is just the opposite sign of our fixed end moment at A. Then we can now proceed solving for the fixed end moment at BC. It is still PL over 8 equals to 40 kilopound. 40 kilopound times 10 feet over 8 equals to 50 kilopound feet. So it is positive, and therefore it is a counterclockwise moment. So this is also a counterclockwise moment. Counterclockwise moment. This is clockwise moment because it is negative. So for CB, and again, it's just the opposite sign of our fixed end moment BC. This one. Negative 50 kilopound feet. So since it is negative, then it is a clockwise moment. Clockwise. since we have the values. I'm sorry for the dogs shouting in here. They are very annoying. Thank you, dogs. So, we already have our distribution factors and fixed end moments at member AB, BA, BC, and CB. So this is our distribution factor 0, 1 and 0.6 and 0.4. So we will be plotting these values now in a table in respect to our beam or the figure we have. So let us reveal now. So yes, this is our distribution factor at AB. Distribution factor at AB. This is our distribution factor at BA. This is our distribution factor at BC equals to 0.4. And distribution factor CB is 1.0. As you can see in here. So let us also plot the fixed end moments we got earlier. So here they are. 100, 100, negative 150, and negative 50. This is the one we plot here. This value, then this value, then this value, then this value. So we plot it from left to right. So to proceed, we will now multiply this fixed end moments to the distribution factor. So 100 times 0 is equals to 0. Negative 100 times 0.6 is equals to 30. And 50 multiplied to 0.4 is equals to, oh no, I am wrong. So it's basically if we see this kind of plotting like they are beside each other, so we will be adding them. So negative 100 plus positive 50 is equals to negative 50. Then this negative 50, we will be multiplying it there. So 0.6, which is equals to 30. And I forgot, we will make the values of our distribution factor into negative. So these are negative values. So negative 0.6 and negative 0.4. This also negative 1.0. So they are negative values, guys. They are negative values. They are negative values. So let's proceed. So negative 100 plus 50 is equals to negative 50 multiplied to the distribution factor at BA 0.6. Then we will put the 30 here. And negative 50 multiplied to the distribution factor of BC 0.4 is equals to 20. And negative 50 multiplied to the negative 1.0 distribution factor of CB is equals to 50. So again, negative 50 multiplied to negative 0.6 is equals to 30. And negative 50 multiplied to the 0.4, negative 0.4 equals to positive 20. So let us proceed now. So this is called our cycle 1. This is our cycle 1. We are going to basically make another following cycles. So we are now on the cycle 2. So the next thing we're gonna do is carry over and divide by 2. So 30 carry over divide by 2 equals to positive 15. So 30 divided by 2 positive 15. So 30 carry over divided by 2 positive 15. 0 carry over divided by 2 is equals to 0. 50 carry over divided by 2 is equals to 25. 20 carry over divided by 2 is equals to 10. Okay, so we will be going to repeat that process again and again and again until we are almost at 0. So we are going to distribute the balance moment again. So 15 again, we will going to multiply this 15 to the distribution factor at this point. So 15 times multiplied with 0 is equals to 0. 0 plus 25 is equals to positive 25. Positive 25 multiplied to negative 0.6. We got negative 15. Then again, we will multiply it to negative 0.4. We will get negative 10. And in here, 10 multiplied to negative 1.0 will basically equal to negative 10. So I am going to reveal all the other cycles. The dogs are very noisy. So let us continue now. Again, after distributing again to the multiplying the fixed balance moment to the distribution factor, we will now proceed to carry over divide by 2 again. So negative 15 carry over divide by 2 equals to negative 7.5. 0 carry over divided by 2 equals to 0. Negative 10 carry over divided by 2 equals to negative 5. Negative 10 carry over divided by negative 2 equals to negative 5. So again, 7.5 multiplied to 0 is equals to 0. 0 plus negative 5 is equals to negative 5 multiplied to negative 0.6 is equals to 3. Again, negative 5 multiplied to negative 0.4 is equals to positive 2. Negative 5 multiplied to negative 1.0 is equals to positive 5. So we will carry over again and divide by 2. 0 carry over divided by 2 equals to 0. 3 carry over divided by 2 equals to 1.5. 5 carry over divided by 2 equals to 2.5. 2 carry over divided by 2 equals to 1. So again equals to 1. So 1.5 multiplied to the division factor at AB equals 0. So it will be 0. 0 plus 2.5 is equals to positive 2.5 multiplied to negative 0.6 is equals to negative 1.5. Again, positive 2.5 multiplied to negative 0.4 is equals to negative 1. 1 multiplied to negative 1.0 is equals to negative 1. Again, carry over. Negative 1.5 carry over divided by 2 is equals to negative 0.75. 0 carry over divided by 2 is equals to 0. Negative 1 carry over divided by 2 equals to negative 0.5. Negative 1 carry over divided by 2 is equals to negative 0.5. So negative 0.5 times 0 equals 0. 0 plus negative 0.5 times 0.6 times negative 0.6 equals to 0.3. Negative 0.5 times negative 0.4 positive 0.2. Negative 0.5 times negative 1.0 is equal to positive 0.5. Carry over again. Carry over 0.3 divided by 2 equals to 0.15. 0 carry over divided by 2 is equals to 0. 0.5 carry over divided by 2 is equals to 0.25. 0.2 carry over divided by 2 is equals to 0.1. 0.15 times 0 equals 0. 0 plus 0.25 times 0.6 is equals to negative 0.15. 0.25 again multiplied to negative 0.4 is equals to negative 0.1. 0.1 multiplied to negative 1.0 is equals to negative 0.1. Again, carry over negative 0.15 divided by 2 is equals to negative 0.075. 0, carry over divided by 2 is equals to 0. Negative 0.1 carry over divided by 2 is equals to negative 0.05. Negative 0.1 carry over divided by 2 is equals to negative 0.05. Repeat the distribution process again. Negative 0.075 times DFAB equals to 0. 0 plus negative 0.05 is equals to multiplied to negative 0.6 is equals to 0.03. Negative 0.05 multiplied to negative 0.4 is equals to positive 0.02. Negative 0.05 multiplied to negative 1.0 is equals to 0.05. So we are now at the 7th cycle. We will then summate all the fixed end moments in all the balance moments in this problem. So 100 to 0 will basically sum them all up. So 100 plus 15 minus 7.5 plus 1.5 minus 0.75 plus 0.15 minus 0.075 is equals to 108.325. 108.325 here. Since it is positive, then the moment is counterclockwise. In this area, again, sum all this balance moment. So from negative 100 to positive 0.03, it will equal to negative 83.32. 83.32. Since it is negative, then it is a clockwise moment. And here 50 up to 0.2, sum again, it will equal to positive 83.32. Since it is positive, it is a counterclockwise moment. And here negative 50 down to 0.05, summate all of them, it will eventually lead to 0. So our moment at CB is equals to 0. Since we are going to solve for the reaction forces, let us proceed into it now. Wait, let me provide a better quality. So here it is. let us reveal it first. There you go. So let us first see the free body diagram. We have RA here and RBL. So what does RBL mean? So it is the reaction force in the left of the point B, or the reaction force B. We have the load here, so this is member A to B, 10 feet away, and the load is 80 kilopound, 5 feet away from B, and 5 feet away from A. So this is positive and a negative moment, as you can see in the sign. So this is positive. Since we have the values now of our fixed moments, or the moment we solved earlier, here we can now solve for the reactions. So summation of moment at D equals 0, assuming counterclockwise positive. So 108.325 plus the 80 kilopound force times the distance 5 feet. So here 5 feet, because it is away from B 5 feet. So our B is located here, minus RA. So why is it minus? It is because our moment is counterclockwise, and RA is resisting it, therefore it will be negative. Okay, that is why it is negative, because it is resisting the counterclockwise moment. So that's why. Then minus 83.32. So it is minus again because we are assuming that the moment is counterclockwise and this moment is clockwise, then it will be negative, equals to 0. Solving for the RA, this equals to 42.5005 kilopound. To solve for the reaction force B at L, let us summate all the forces. Vertical equals 0, assuming downward forces positive. So RA plus RBL minus 80. So RA, RBL, they are positive because they are going upwards. Then we have 80 as the resisting force, therefore it is negative right there, equals 0. So substitute the values, 42.5005 kilopound plus RBL minus 80 kilopound equals 0. So we have RBL equals to 37.4995 kilopound. Let us now proceed to segment BC. Segment BC. Let's proceed. So, we have again RBR in here. So, this is the right side of our reaction force B. So, this is the left and we are on the right now. So, we have this fixed end moment, 83 moment at BC, as 83.32 kilopound-feet, and our load 40 kilopound, acting upon at the center again. So it is still 5 feet away from RBR and 5 feet away from reaction C. And the total span is 10 feet. So let us solve for RC. The summation of moment at B equals 0, assuming counterclockwise still positive. So substitute the value. I create the moment of equation, 83.32 minus 40 kilopound times 5 feet plus reaction at C multiplied to the total span of the member. So 10 feet equals to 0. So our RC is equals to 11.668 kilopound. So let us not forget the reaction force at B, right side. So RBR. So again, summation of forces, vertical, is equal to 0, assuming upward forces are positive. RBR plus RC minus 40 is equal to 0. So why is it like that? It's because, again, RBR is an upward force, RC is an upward force, and 40K is a resisting force, or resisting force, downward force, so it will be negative. That's why. So equals to 0. So substitute the values we got earlier. RC here, RBR plus 11.668 kilopound minus 40 kilopound is equals to 0. And then the value will be 28.332 kilopound. So to solve for the total reaction force at B, we will add the reaction force at B left and right. So substitute the values, RBL, RB right, add them. So 37.4995, 28.332 kilopound. Sum both of them, then our RB will be equal to 65.8315. So we have completed now and solved for all the reaction forces. So let me square this one and this one. So our final answer RA is equals to 42.6 0.5005 kilopound RB 65.8315 kilopound and RC 11.668 kilopound. So let us proceed now for the next problem. So our problem 2 is another beam with an overhang beam with a total span of 19 feet. 6 plus 9 plus 4 equals 19 feet. So we have a load here at point D, 30 kilopounds, and a distributed load at member BC, 10 kilopound per feet. 10 kilopound per feet. So in the span of 9 feet. And we don't have a load in here, so we'll just focus in this area and it will become easy because we don't have load here. So again, let us solve for the distribution factor. So our objective in this problem is to compute the member and moment. So distribution factor dF is equals to member stiffness over summation of all the member stiffness, wherein member stiffness is equals to 4 EI over L, where L is length, I is the moment inertia, and E is the elasticity, I modulus of elasticity. So in this problem, let us assume that EI is constant. So let us solve now for the member stiffness first. So our member stiffness AB is equals to 4 EI over L. 4 EI over L. So substitute the value for EI, or EI is constant. Our length is 6 here, 6 feet. And substitute in here, then 4 EI over 6 equals to 2/3 EI. Now, our member stiffness at BA is also equals to 2/3 EI. 2/3 EI. And for our member stiffness at BC, so I'd like to introduce a new process in this. This is called the modified stiffness for simple and support beam. So this is basically a simpler form than the other one we used earlier in the problem 1. So It states that a beam which is simply supported at the far end is only three-fourths as stiff as the one that is fixed. If the stiffness factors for end spans that are simply supported are modified by three-fourths, here, three-fourths, the simple end is initially balanced to 0. No carryovers are made to that end afterward, and the same result will be obtained. So it is called the modified stiffness for simple end support beams. So we have this originally KBC 49EI. We will just simply multiply it by 3/4. So remember, KBC or member stiffness BC can be a simply supported beam by eliminating or cutting this portion overhang beam and turning it into a exterior roller support end here. So basically we will eliminate this section and solve for its moment so that we will have an exterior ending here. Moment that is negative. So this one is also to be multiplied by 3/4 equals to 1/3 AI. So remember why our DFAB is 0? It is because A is 0. I mean A is a fixed-ended point. Now solving for DFBA, we have member stiffness BA over the summation of all the member stiffness. So 2/3 EI over 2/3 EI plus 1/3 EI equals to 2/3. Next one is DFBC. Member stiffness BC over the summation of all members stiffness is equals to 1/3 EI over 2/3 EI plus 1/3 EI equals 1/3. We can now proceed in solving the fixed end moment. Fixed end moment. So at FEMAB equals 0 and FEMBA equals 0. So why? It is because we don't have any type of loads in this member AB. We don't have any type of loads. That's why it is 0. So we have here FEMBC and FEMCB to be using this formula. So let us go back to our table of figures and its types of loadings. So where is it? So here. As you can see, this is a fixed-ended structure and has a distributed load acting upon the whole span of the member of the beam. So it will always be WL squared over 12, where W is the uniformly distributed load and L is the length, and over 12. So again, sign convention. This is a negative moment because it is clockwise, and a positive moment because it is clockwise. So let us get back to our problem 2. Our FEMBC is equals to WL squared over L. So this was in the figure I showed you just now. So 10 is the distributed load. Here 10 distributed load, and 9 is the span of the member, or the span of the distributed load, and over 12. So square, this is squared, guys. So it's equals now to 67.5 kilopound feet. So FEMCB is just the opposite sign of our FEMBC. So it is the opposite sign. So negative. That is negative 67.5 kilopound feet. Now since we eliminated, just as I said earlier, we eliminated the overhang beam. So, and we calculated for the moment MCD. So it is to be solved by 4 for the distance, 4 feet, times the load, which is 30 kilopound. 30 kilopound. Now it is equals to 120 kilopound feet. Let us now reveal our table. So distribution factor at AB equals 0. Distribution factor at BA equals to 2/3. Here, 2/3. Distribution factor BC equals to 1/3. Here, 1/3 EI. And the distribution factor at CB equals to 1.0. Oh, it become 1.0 because we eliminated this portion already. So it is now a full exterior roller support end. We will not put any distribution factor anymore here because we put it all at DFCB, distribution factor CB. So that is why we solve for the here MCD, which is a counterclockwise moment, and therefore it should be positive 120 kilopound feet. Again, let us plot all the F fixed end moment we solved earlier. So FEM AB is equals to 0. FEM BA is also equals to 0. FEM BC is equals to 67.5. FEM CB is equals to negative 67.5 kilopound feet. So, our moment 120 is from here, the one we solved earlier, the moment at CD. Now, let us distribute again or balance the moments. So, 0 times 0 is equals to 0. 0 plus 67.5 times negative 2/3. Again, we will assume these distribution factors as negative. Okay? Negative. These are negative, guys. Okay? So 0 plus 67.5 is equals to positive 67.5 multiplied to negative 2/3, then it will equal to negative 45. Now, positive 67.5 multiplied to negative 1/3, negative 1/3 is equals to negative 22.5. Negative 67.5 plus 120 is equals to 52.5 times 2 negative 1.0. It will equal to negative 52.5. So again, distribute, carry over the moment. Negative 45 carry over divided by 2 is equals to negative 22.5. 0 carry over divided by 2 is equals to 0. Negative 52.5 carry over divided by 2 is divided by negative 2 is equals to negative 26.5. So here we will stop here because we already applied the modified stiffness method, the one we did earlier, multiplying the simply supported member stiffness to 3/4. So we will leave them here, no more anymore in there, because it will still lead to the right answers. So, okay. So again, negative 22.5 multiplied to distribution factor AB 0 is equals to 0. 0 multiplied to negative 2/3 is 0 plus negative 26.5 multiplied to negative 2/3 is equals to positive 17.5. And negative 26.25 multiplied to negative 1/3 is equals to positive 8.75. So let us distribute again. I carry over 17.5 divided by 2 is equals to 8.75. 0 carry over divided by 2 equals 0. And it will end in there because we have here 0. We don't have something in here, so it is basically 0. So 0 and 0, 0, 0. Now we will now sum from 0 to 0. So sum all these values. So negative 22.5 plus 8.75 is equals to negative 13.75. So 0 and here also negative 45 plus positive 17.5 is equals to negative 27.5. Now, in here, 67.5 minus 22.5 minus 26.25 plus 8.75 is equals to 27.5. And lastly, here, negative 67.5 minus 52.5 is equals to negative 120. And bring down this 120 in here. Now, we have solved the problem. We have solved the fixed end moments. So we have here negative 37.75, negative 27.5, positive 27.5, negative 120, positive 120. So this is negative because it is clockwise. This is also negative because it is clockwise. Positive because counterclockwise. Negative because clockwise. And counterclockwise positive. That's all, guys. Thank you, and I hope you learned something. The next reporter will be Cuartero, the reporter of three-moment equation.
Or vertical support mo siya 6 multiplied by the height of the left side or height of the L over by length L plus HR height of the right side over by LR. So this is the general equation gigidrive na gikan for example during a beam. This side is the moment left, which is RML. This side is the MR or the moment right. This is the moment center. So naman tayo ni moment center na to duha na ay pa left o na ay pa right, no? So if memorize ang general equations, makuha na to ani duha ka equation, which is the if E is constant, ato lang simply i-remove ang E gikan sa general equation, no? Then if E and I is constant, ato rin pong i-remove si E and I gikan sa atong general equation para makuha ta new formula para sa E and I is constant. So before ko maghataw example, ako sa pailailan niyang types of loading. Ang iyahang formula gamiton if magkuha ka sa 6A bar A over L o sa 6A bar B over L. If concentrated load, mo na imong gamiton nga equation or formula. Concentrated load anywhere of the span, mo na imong gamiton nga formula sa 6A bar A over L, which is the PA over L multiplied by L squared minus A squared. If 6A bar B over L, among kuhaon, ang iyang formula is P multiplied by B over by L times L squared minus B squared. So, sa concentrated load at the midspan, isa lang iyahang formula both sa 6A bar A o 6A bar B over L, 3PL squared over 8, mo rin magamiton nga formula. Same sa uniform load, isa rin po ang formula niya. Uniform load over the entire span, ang formula niya is WL cube over 4 sa both 6A bar A o sa 6A bar B over L. Then increasing triangular, the decreasing triangular o napoy isosceles triangular load, no? Then kinisab na sa time moment load at any point on the span. If na makasugatan ni atong gamiton sa 6a bar a over L, kini nga formula, negative moment, no? Negative m divided by L multiplied by 3a squared minus L squared, o makasugatan ni ang atong 3a bar b mo na iyang formula, positive ml, no, m over L multiplied by 3b squared minus L squared. Then atong general uniform loading mo na atong gamiton sa 6a bar A sa 6a bar B nga formula. Okay, natay example number 1, no? When E is constant. So natay beam which is na duha concentrated load o na uniform load, no? So sa span AB, duha ka concentrated load which is 150 kN o 100 kN. At nasya sa 2 meters and 2 meters, so nabahin siya. So when E is constant, sa atong formula ganina, naduman nimo ato rang i-remove si E sa general formula. So mo ni siya, si ML over L mo na ito nakuha, then over by IL plus 2MC multiplied by LL over by IL plus LR over by IR plus MR LR over by IR plus 6A bar A, no, divided by IL times LL plus 6A bar B divided by IR LR equals, no, 6E then HL over L plus HR then over LR. Since kay wala man tay vertical movement of support, so kini siya ato ni siyang i-crush, ato ni siyang i-automatic 0. Karon ato una kuhaon si 6A bar A over by IL times LL. So since concentrated load man siya, based sa atong gihatag nga formula ganina, ang formula sa concentrated load 6A bar A over L is equals to P times A over L times L squared minus A squared. So 150, si P atong load is 150 times A is 2 meters divided by 6 span niya, then multiplied by 6 squared minus 2 squared plus ang concentrated load nga 100 kN ato yung i-add multiply by na siya sa 4 meters. 100 times 4 divided by 6 then times 6 squared minus 4 squared. Ang atong 6A bar A over L is equals to 2933.333. Sa atong 6A bar B, which is this side, no, this side. So since this is uniform load, ang atong formula is WL cube over 4. So 6A bar B over L equals to WL cube over 4 equals to 50 ang atong weight. Ang atong length is 5 cube over by 4. So 6A bar B over L is equal to 1562.5. Then arito sa atong formula nga atong gigamit ganina, no, sa gikan sa general formula, atong gamiton ang E constant formula which is kini. So atong i-substitute moment left multiplied by 6 over by 2I plus 2MC times 6 over 2I plus 5 over I plus MR multiplied by 5 over I plus ang atong 6A bar A over L mo ni siyang 2933.33 over by 2I plus 1562.5 which is our 6A bar B, no, then over by I. Since kay ang I is ato siyang i-factor. So 1/2 times 6 ma squared, 6 ma over by 2 plus 2 mb. So if malibog ka nga nung mc diri, mb diri, so kini no, si ml is equal to ma, si moment left is sa atong graph si moment A. Ang atong moment center si moment B. Ang atong moment right si moment C. No? So dire 2mc pagabot dire 2mb. So isa mo ra gyud na siya kay moment center man siya. No? So akong balikon 1/2 times 6ma over 2 plus 2mb times 3 plus 5 plus moment C, no? Times 5 plus ang atong 6a bar A 2933.33 plus ang atong 6a bar B is 15.62.5. Then since kining si moment A nato og si moment C is equal to 0, kay ini moment diri sa hinge ug sa ruler kay equals to 0 man, ato siyang i-cancel. So atong nabilin 2mb times 8 plus ato ni silang atong solve, no, 2933.333 divided by 2 plus 1562.5 is 3029.1665. So maning 2mb times 8 plus 3029.1665 equals to 0 comes up with 16mb plus 3029.1665 equals to 0. Ang atong mb is equals to negative 89.323 kilonewton per meter. Then ang hita sa tong FBD or sa tong free body. So kung ano to ang reaction sa reaction sa A, no? So mo ting span AB span mo siya atong load 150 o 100. Then ang atong moment, no? Ang atong MB mo ning 189.323. So summation of moment B equals to 0 plus positive upward direction. So negative RA times 6 plus 150 times 4 plus 100 times 2 minus 189.323 equals to 0. Ang atong reaction size is 101.779 kilonewton. Sa force vertical, positive upward, RA minus 150 minus 100 plus ang RBL na to or atong right dire reaction sa B or left, reaction sa B left naman siya equals to 0. So ang RA atong substitute 101.7795 minus 150 minus 100 plus RBL equals to 0. Ang atong RBL equals to 148.2205 kilonewton upward direction, no? So sa FBD nato diri sa pikas kini sa uniform load. So natong pikas diri atong moment B ganina. So 189.33 50 kilonewton load. Itong span 5 meters RBR then RC. So summation of moment B 0 plus positive upward direction. So 189.323 minus 50 times 5 times 2.5, this is 2.5 2.5 plus RC times 5 equals to 0. So RC equals 87.1354 kilonewton up. Then sa atong force vertical equals to 0 upward direction, RC equals to 50 times 5 plus RBR, substitute ito si RC is 87.1354 minus 50 times 5 plus RBR is equal to 0. Atong RBR is 162.8646 kilonewton. So duha man ang atong moment sa R kay man left and right man. So atong kuan ang reaction at B total reaction at B. So mo ni si pagkuha na is dali ra. Si reaction at B left plus reaction at B right, i-add na nato sila. So 148.2205 plus 162.8646. Ang atong reaction at B is 311.0851 kilonewton. So, okay, sa atong example number 2, natay increasing load, natay concentrated load, natay uniform load, no? Natay increasing load nga 1,400, concentrated nga 900 newton, o uniform load nga 800 newton per meter. So, this is if E is constant, no? Sa atong gikan sa atong general equation, no? If E is constant, so mo ni atong gamiton nga formula. So, ML times LL or sa moment left times length left plus 2 MC moment center multiplied by the sum of length left plus length right plus MR times LR plus 6A bar A over L plus 6A bar B over L equals to 0. So, first, adiserta mo proceed sa atong formula, sa atong ihatag equation. Ato saan na yung pangitaon si 6A bar A o si 6A bar B over L. No? So, atong 6A bar A ani is this one. Ang atong increasing load. Nga si 1,400 Newton per meter. So, since this is increasing, sa akong ipakita ganina, or sa atong copy sa types of loading, if ang atong count si 6A bar A, si increasing load, ang iyahang formula gamiton, 8 times W times L cube over by 60. So, 6A bar A over length left equals 8 times W times L squared, L cube over by 60 equals by 8 times 1,400 times 4 nga iyang length cube over by 60. Ang atong 6A bar A is 11,946.67 Newton per meter squared. Ang atong 6A bar B, which is this side, duha man siya atong magamit ani ang concentrated load o ang uniform load. So sa concentrated load, atong formula gamiton is ang P times B, no, over by L, then L squared minus B squared plus ang atong uniform load W D squared over 4L times 2L squared minus D squared. So sa 6, to substitute sa atong 6A bar B over L equals 900 Newton times 3 divided by 4 times 4 squared minus 3 squared plus sa atong uniform load 800 times 2 squared over by 4, then ang atong length is times 4 na to siya, then multiplied by 2 times 4 squared minus 2 squared. Ang atong 6A bar B over L equals to 10,325 Newton per meter squared. So, dirita sa atong formula, itong if EI is constant, since si moment left o si length left equals to 0 o si moment right o length right is equals to 0, so ato siya ilargo substitute as 0, no? So 0 plus 2 moment center times 4 plus 4 plus 0 plus ang atong 6A bar A mo ng 11,946.67 plus ang atong 6A bar B, which is 10,325, then equals to 0. So, ato ni solve sa calculator, ato makuha na ang atong moment center is equals to negative 1,391.98 Newton per Newton times meter.
Hi everyone. My name is Vivian Sylvester and Duran, and I'm going to discuss to you about the analysis of frames using the portal method. The portal method is an approximate method of analyzing building frames. And in this method, we follow three assumptions. The first and second assumption are somewhat the same, where the first assumption states that an inflection point occurs at the mid-height of each column. This means that if we have a column here, and this is its length L or its height L, the inflection point is located at its mid-height or at L over 2. And it is also said that at L over 2 or at the inflection point, the moment is equal to 0. Same goes for our second assumption, which states that an inflection point occurs at the midpoint of each girder. So if this is our girder and this is its length L, same as before, the inflection point is located at L over 2, which is its midpoint. And at midpoint, or at the inflection point, it is said that the moment is equals to 0. Then we'll move on to our third assumption, which states that the total horizontal shear at each story is divided between the columns of that story such that the interior column carries twice the shear of the exterior column. What does this mean? If we have a frame here, and this is our columns, and this is our girder, this is what our assumption says, that the interior columns carries twice the shear than of that the exterior columns. So if we have a shear here, which is V and V, which are exterior columns, the interior columns says that it carries twice, so we multiplied it by 2, or twice the shear than the exterior columns. To further understand this, we'll have some examples. For our first example, let's have a one-story frame, where the length of the columns are equal to 8 meters, and the distance between the columns are also 8 meters, or the length of the girder are 8 meters. And in this frame, a 40 kN lateral load is applied to it. So in solving the portal method, we follow certain steps, where we first find the column shear, next is the column moment, followed by the girder moment, and last is the girder shear. So first thing we're going to do is we locate the inflection point as what we've assumed, as what the assumption says, that the inflection point is located at the midpoint of the girder and of the columns. So if our column is equal to 8 meters, that means that our inflection point is located at 4 meters. And let us label this point as point H, I, and J. And this is located 4 meters. Next is also the location of the inflection point of our girder, which will be labeled as point K and L. The next thing we're going to do is solve for the column shear. To solve for the column shear, we then go back for our assumption where the inner, this one, right here, the inner shear is twice than that of the exterior shear. So if we have a shear here, which is V, as our exterior shear, our interior shear is twice of that, which is 2V. Now, in order to solve for our shear, we just use the summation of horizontal forces equals to 0, where 40 kN 40 kN 40 Newton is equals to V is 1 plus 2V plus V, or 40 kilonewton is equals to 4v. In order to get our shear, we only divide this by 4. 4. That means our shear, or the shear at the exterior columns, is equals to 10 kilonewton. And twice that is our interior shear, which is equals to 20 kilonewton. So let's put that here. This will be 20 kilonewton. And here, 10 kilonewton. Same goes for here. Equals 10 kilonewton. Now we've done solving for the column shear. The next thing we'll do is finding the column moment. In getting the column moment, we just need to multiply the shear to the half of the length of the column. So if our length is 8 meters, half of that is 4. And then we multiply 4 to 10, then we'll get our column moment. And our column moment, we always assume that the moment on the columns move counterclockwise, like this one. The movement of the moments on the columns are counterclockwise. And like I said, to get the moment, we just multiply the shear times the half of the length of the column, which is 4 meters. So 10 times 4 is equals to 40 kilonewton meter. Don't forget the units. So this is 40 kilonewton meter. Same goes for, as this is same goes for the one below. As this is a one rotation, so that means that the value here is just equals to the value here. So if this is 40 kilonewton, then it will follow that will also be 40 kilonewton meter. Then we'll just apply what we did here to this to the inner or the interior column. Our interior column has a shear of 20 kilonewton, and multiplied by the half of its length, which is 4 meters, then we'll have an 80 kilonewton per meter moment. We'll jot this down: 80 kilonewton meter, 80 kilonewton meter. Then we'll move on to the last column. Same as before, it has a shear of 10 kilonewton and one half of its length is 4. So automatically, it has a moment of 40 kilonewton meter. Same goes below, 40 kilonewton meter. Now we've done solving for the column moment. The next thing we'll solve is for the girder moment. To solve for the girder moment, we first start here. And for the girder moment, we will assume that the movement of the moments on the girder moves clockwise. Why? As what we've learned so far, in order for the moments to be in equilibrium, each side would have an equal force. So if there is a counterclockwise movement here, clockwise movement should also counter it with the same value. So therefore, if this is 40 kilonewton, 40 kilonewton meter moment, the counterclockwise flow of our the clockwise flow of our girder will have also a value of 40 kilonewton meter. And as the same before, it's because this is a one rotation, that means the value here is also equals to the value here. So this would be 40 kilonewton meter. Now, in order to solve this one, where there is a joint um, where there is a moment here going here, which is 80 kilonewton meter, and a moment going here, which is also 40 kilonewton meter, and another one here. So this one is missing. In order to solve this, we just use the summation of force for the summation of moments is equals to 0. Summation of moment is equals to 0, where counterclockwise, I mean clockwise is equals to counterclockwise. So what are the clockwise here? So our clockwise here is 40 kilonewton meter plus this is also moving clockwise plus. So let's name this one as moment EL. Moment EL is equals to 80 kilonewton meter. Therefore, our moment EL is equals to 40 kilonewton meter here. Again, same value here, 40 kilonewton meter. Now we've done solving for our girder moment. The next thing we'll solve is our girder shear. So how do we solve our girder shear? In order to solve for our girder shear, we just need to add the moments of our girders divided by its length, or just twice the moment over L. So here, the moment is 40, so 2 times 40 divided by 8. So our moment will be equal to 2 times 40 is equals to 80 divided by 8, which is equals to 8 kilonewton. So our shear, or our girder shear, is equals to 10 kilonewton. Same here, 40 plus 40 divided by 8 meters, or 40 times 2 divided by 8 is just equals to 10 kilonewton. Now we've done solving for our column shear, our column moment, and our girder moment, and also our girder shear. So we find the missing values of our frame. This means that we've done a great job, an amazing job. So next we'll be solving another example, which will be a 3-story frame. So our next example would be a 3-story frame, where the length of the columns of each story is 3 meters, and the distance of the girders are 6 meters, 5 meters, and 4 meters. And a 10 kilonewton load is applied on the uppermost story. 15 kilonewton force is applied on the second story, and 20 kilonewton force or lateral load is applied on the first story. So like before, the first thing we should do is solve for the column shear. And to solve for the column shear, we must first start at the top. We must first isolate this part here. So same with our assumption, the inner shear is twice than that of the exterior shear. So the shear here at the inner shear is 2V, and here V. So to solve for our shear, we'll just use the summation of forces horizontal equals 0, left is equals to right. So 10 kilonewton is equals to V plus 2V plus V, or 10 kilonewton is equals to 4V, where V is equals to 2.5 and 2V is equals to 5 kilonewton. So we'll put the values here. 2V is 5 kilonewtons. Here is 2.5 kilonewtons. Also here 2.5 kilonewtons. Once we're done at the top, we'll move at the bottom. And here, same as above, we'll get the shear of the interior and exterior columns. Same. And when we get the shear here at the exterior columns, we'll include the force applied on the uppermost shear plus the force applied on the story that we're currently analyzing. So here, same, summation of forces horizontal equals 0. Left is equals to right. So 10 kilonewton plus 15 kilonewton is equals to, this one is shear, 2V, 2V, also V. So V plus 2V plus 2V plus V is equals to 6V. So 25 kilonewton is equals to 6V. I'll divide both sides by 6 in order to get our shear. And our shear will be equals to 4.167. And our due shear would be 8.334. And we'll put the values in our diagram. So this is equals to 4.167, 8.334, 8.334, and then 4.167. Now we'll move on to the first story. Same, we'll add all the horizontal forces here, and in order to get our shear at the first story. So summation of forces horizontal equals 0, right? 10 kN plus 15 kN plus 20 kN is equals to the shear, which is V, 2V, 2V, V. So same, that is equals to 6. Now 10 plus 15 plus 20 is equals to 45 kilonewton equals 6V. Divide both sides by 6, and we'll get the shear is equals to 7.5 kilonewton. And twice that is 15 kilonewton, which is the shear at the interior columns. So 7.5 kilonewton, 15 kilonewton, 7.5 kilonewton, oh no, sorry, this is 15. This is 15 kilonewton and 7.5 kilonewton. Let's just correct this for a little bit so everything will be clear. This is 15 kilonewton. Don't forget the units to avoid confusion. So, now we're done solving for the column here. Next step is solving for the column moment. like what we've done on the first example, in order to get the column moment, we must first, I'm sorry, let's make this uh, some error. This is, let's make this 6 meters, 6 meters, and 6 meters. So yeah, there's some few corrections, but yeah. So yeah, to solve for the column moment, we just need to multiply the shear half of the length of, multiply the shear to the half of the length of the columns. And like what I said before, we will assume that the movement of the moments on the columns are counterclockwise. So here, everything's moving counterclockwise. Counterclockwise. Also here. Okay, so to get the column moment, multiply 2.5 to the half of 6 meters, which is 3 meters. So 2.5 times 3 is equals to 7.5 kilonewton meter. So like before I said, this is a one rotation, so the value here would be the same as the value below. It is 7.5 kilonewton meter. And we just repeat what we've done here. 5 times 3 is equals to 15 kilonewton meter. And also to the exterior column, this would be 2.5 times half of 6, which is 3. That would be equal to 7.5 kilonewton meter. 7.5 kilonewton meter. Next, we'll move on to the second story. Same as what we did at the top. 4.167 times half of 6, which is 3 meters. Well, that would be equal to 12.501 kilonewton meter. 12.501 kilonewton meter. Next here, 8.334 times 3 would be equal to 25.002 kilonewton meter. 25.002 kilonewton meter. As this has the same values, so just copy it. 5.002 kilonewton meter. 25.002 kilonewton meter. So here, same as the other side, 4.167 times 3 is equals to 12.501 kilonewton meter. 12.501. Sorry, 501 kilonewton meter. Now we'll move on to the first story. So 7.5 times 3 would be 22.5 kilonewton meter. Copy that here. Again, the value here and here are the same, for it is only one rotation. Next here, 15 times 3 would be 45 kilonewton meter. 45 kilonewton meter. This has the same value, so 45 kilonewton meter. 45 kilonewton meter. So the last part, the exterior column, 7.5 times 1/2 of the length of the column, which is 3. That would be 22.5 kilonewton meter. 22.5 kilonewton meter. Now we've done solving for the column moments. The next thing we'll do is solve for the the gear moments. So to solve for the gear moment, we'll start first at the upper left here. So like I said before, the counterclockwise motion of this section here needs an opposite direction of force in order for this to be in equilibrium. So if there's an counterclockwise motion here, so it must follow that a counterclockwise motion would also be will is applied here in order for the frame to be in equilibrium. So everything here would be on a clockwise motion. So clockwise, clockwise, clockwise. Also here, clockwise, we'll jot this down. Clockwise. So that's it. So, like I said, an equal force would be applied here for it to be equilibrium. So if this is 7.5 kilonewton meter, this follows. It follows that the value here would also be 7.5 kilonewton meter. Then, as before, this would have the same value, 7.5 kilonewton meter. Now, how to solve this one? We'll just use the summation of forces moment where counterclockwise is equals to clockwise. So here, this is the figure. A counterclockwise motion of 15 kilonewton is applied here, and a clockwise motion of 7.5 kilonewton is applied here. This is also clockwise, so summation of moment equals 0. Summation of moment equals to 0, where counterclockwise is equals to clockwise. So 15 kilonewton meter is equal to 7.5. Let's name this as x plus x. So that means x is equals to 7.5 kilonewton meter. 7.5 kilonewton meter. So this part here has the same value. So we'll just copy it down. Done. So move on to below. Same here. We'll just use the summation of moments. Let's see, this one. This has a counterclockwise motion, also here. So 7.5 kilonewton meter, 12.501 kilonewton meter. So let's name this as x. So summation of moment equals 0, where counterclockwise equals to clockwise. So 7.5 kilonewton meter plus 12.501 kilonewton meter is just equals to x. So that means x is equals to 20.001 kilonewton meter. So the value here is 20.001 kilonewton meter. Same here, 20.001 kilonewton meter. Now here, how to solve this one? Same as before, summation of moments equals 0. So here, Here's a counterclockwise motion of 25.002 above 15. Here is 20.001. So summation of moments equals 0. Counterclockwise equals clockwise. So 15 plus 25.002 is equals to 20.001 plus x. Let's name this as x. So x is equals to 20.001 kilonewton meter. So just this now 20.001 kilonewton meter. Same here, 20.001 kilonewton meter. Now for the other side, just do the same. A value of 7.5 moving counterclockwise here, 7.5. Then another counterclockwise below, which is 25.002. So here is 20.001. Now to solve this, just repeat what we did. Summation of moments equals 0, where counterclockwise is equals to clockwise. So 7.5 plus 25.002 equals 20.001 plus x, where x is equals to 12.501 kilonewton meter. So here 12.501 kilonewton meter, 12.501 kilonewton meter. Now we'll move on to the first story. So same as before, to get the moment here, just use the summation of moments equals 0, clockwise equals counterclockwise. So let's name this x. X equals to 12.501 plus 22.5. X is equals to 35.001 kilonewton meter. So the value here is 35.001 kilonewton meter. Same here, 35.001 kilonewton meter. So here, same as we did before, summation of moments equals 0, clockwise equals to counterclockwise, 35.001 plus x equals 25.002 plus 45 kilonewton. So x would be 35.001 kilonewton. Here 35.001 kilonewton meter, 35.001 kilonewton meter. Next up is here. So just repeat the same process again. 25 summation of moments equals 0, counterclockwise equals to clockwise, 5.002 plus 45 equals 35.001 plus x is just equals to same value, 35.001 kilonewton meter. So yeah, 35 value. I'll just put this here. 35.001 kilonewton meter. So about this one. So here we'll just same. We'll just add some summation of moments. So summation of moment equals 0. So 12.501 plus 22.5 equals x. So x is equals to 35.001. Here, 35.00001 kilonewton meter. Now we're done solving for the gear moments. The next thing we'll do is solve for the girder shear. So how to solve for the girder shear? We just need to add the two moments of the girder divided by its length, or just twice the moment divided by its length. So here you go. So first we'll solve this one. So 7.5 or twice the moment times 2 divided by the length of the girder, which is 4 meters divided by 4. Okay, this would be equal to 7.5 times 2 divided by 4 is equals to 3.75 kilonewton. So the value of the girder shear here is 3.75 kilonewton. So we'll move on here. Same process. Twice the shear divided by the length. The length here is 5 meters. So 7.5 times 2 divided by 5. That would be equal to 3 kilonewton. So shear here is 3 kilonewton. Next, we'll go down to the second story. So here, same process. Twice the moment of the girder, which is 20.001 times 2 divided by 4. That would be 20.001 times 2 divided by 4. That would be equal to 10.0005 kilonewton. So the value here is 10.0005 kilonewton. Next, we'll move on to this side. So same process. Twice the shear, 20.001 times 2 divided by 5. That would be equal to 8.0004 kilonewton. 8.0004 kilonewton. Now to this side, the girder shear here is 12.501, right? Times 2 divided by the length, which is 6 meters, divided by 6 meters. The value will be equals to, oh no, change both ends, 4.167. 4.167 kilonewton. 4. No, it won't right. So let's move to black open. Okay. 4 point. What was that? 167. 167 kilonewton. Now we're done at the second story. We'll move on to the first story. So same process. Twice the moment, 5.001 times 2 divided by 4, which is its length. That will be equal to 17.5005 kilonewton. So 17.5005 kilonewton. Newton. Same here. Which is 35.001 times 2 divided by the land, which is 5. That would be equal to 14.0004 kilonewton, and 14.0004 kilonewton. And the last one here would be 35.00. Oh no. Oh yes. Same value. 35.001 times 2 divided by 6. That would be 5.001 times 2 divided by 6, which is 9. That would be equal to 11.667 kilo. 11.667 kilo. Now we've done solving for the column shear, done solving for the column shear, the column moment, girder moment, and girder shear. We could also use, once we have had all of these, we can also use these values to get the actual load or the actual force of each section. So yeah, we can add something here like the axial force. So how to get the actual force? Okay. To get the actual force, we just need to use the vertical equation of equilibrium. So here. So let's consider section MF. This right here. This right here is section MF. So here, this is M and this is F. Section here, so yeah. And a shear force of 3.75 kilonewton is on here. So the force on MF would also be equal to 3.75 kilonewton. How? We just use the summation of forces vertical equals 0, where upward is equals to downward. So, next, move on to the lower part. On the axial load FE. So yeah, copy this down. This one, the shear force equals to 3.75 kilonewton, and here the shear is 10.0005 kilonewton. So what we're finding now is the axial force at this one is MF. So actual force of FE. To solve that, we just need summation of forces vertical equals 0. So FE is equals to 3.75 plus 10.0005. FE is equals to 3.0005 3.75 plus that would be equal to 13.7505 kilo Newton. So here 13.7505. So yeah, just here. One. Next we'll move on to this section. EA. So same as before. Here there's a shear force of 3.75 kilonewton. Here 10.0005 kilonewton. And here there's a force of 17.5005. Here 17.5005 kilonewton. Now we're finding the force, the actual load here. That would be force F. No, I mean EF force. I mean EA force. EA or the actual load EA. Actual force EA. Same. So yeah, same as before. Summation of forces vertical equals 0, upward equals downward. So 3.75 plus 10.0005 plus 17.5005 is equal to EA. So FEA just equals to 31.251. 31.251. Don't forget the unit, kilo. Okay, now we'll move on to the other side. Here, we'll move on to this section. This one right here. So that would be like this, where shear force of 3 kN is applied here in this one. And here, of course, we have this force here is 3.75. Downwards is 3.75. Now we're finding the actual force and J. So to solve that, summation of forces vertical equals 0, where upward is equal to downward. So 3.75 plus F and J is equals to 3, meaning force NJ is equals to negative 0.75. The value is negative, so that means that our assumption that the actual force is going downward is wrong. So F and J is equals to 0.75 going upwards. So we will change the sign here. Instead of down, they should go upward. Okay. Now we'll move on to the part below it. So again, we draw the diagram. Here, 3 kilonewton is applied here. Here, a shear force of 8.0004 kN is applied. The force here, which is going downward, was that it was 13.7505. So we'll just copy that here, 13.7505. kilonewton. Before we said now let's assume this one as force going upward. Now, same as we did on the other side, summation force is vertical equals 0, upward equals downward. So 3kn plus 8.0004 kn plus this is force J JF force JF equals 0. So force JF was 13.7505. So force JF is equals to 2.7501 kilonewton. So our assumption that the axial load is going upward is correct. So 2.7501 kilonewton. Okay, then we'll move on to the other side, the part here. This one, to get the axial force FB. So to get the actual force FB, need to draw the diagram again. Here, here, here. So yeah. The value here we have 31.251 kilonewton, and what we're missing is the force axial, which is force FB. No, this is wrong. Let's assume that the force is going upward to be consistent with our other forces. So yeah, going upward, and going upward. The value here is 3 kilonewton, 8.0004 kilonewton, and 14.004 kilonewton. We add it up. Summation of forces vertical equals 0. FBD would be equal to 6.2502 kilonewton. Okay. Next, once we're done here, we'll move on to this part, this section here. So to solve that, again, we draw first a diagram here. This one. So now that we have values here, this one is going up, this one is going up, and a shear, this one, of 4167 kilonewton supplied here, and the value here is 13.7505, and here is 2.7501. That's what the values here came from. This part, see, 2501 and 13.5. Just need to copy that here. And yeah, same as before, summation of forces vertical equals 0. Solving that, upward, forward, downward. Let's just name this x. So the value of x would be, if we solve this one, 13.7505 equals to 2.7501 plus x plus 4.601 will be equal to 6.8334 kilonewton. Now we're done here, we'll go down below. So again, we'll need to draw down the diagram and be consistent as much as possible. Okay, this one. So shear of 4.167 is applied here, and also here, or shear of 11.667. Where did we get this value? Here. We get this value at here, this one. So yeah, again, this one is going downward, the force here, which is equals to 31.251. This here is 6.2502. And in order to get this one here, this one's going upward. Let's assume this is going upward. You just need to summation of forces vertical equals 0, or downward. This one's upward, 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 downward. To get the value of 9.1668 kilonewton. Now we're done here. We'll move on to this side here. To get the actual force here, you just need to do what we did on the other side, like this one. For that section, an actual force of 4.167 is applied. So therefore, the value here is also 4.167. For the summation of forces vertical equals 0, or upward is equals to upward. So that's why it is equal to 4.167. Next is this section. So a force of 4.167 kilonewton. Here is 11.667 kilonewton. This one, 11.667 kilonewton. Going upward, going downward. So same. Summation of forces vertical equals 0. Upward equals downward. So 4.167 plus 11.667 is equals to the axial force at this side. So in A, that would be equal to 15.834. Now we solve not just the columns here.
Good evening. My name is Alvin Kyla Horserada, and my topic is about analysis of determinate frames using cantilever method. So first, what is a cantilever? A cantilever is a rigid structural element that extends horizontally and is unsupported at one end. And a cantilever can be formed as a beam, plate, truss, or slab. So, example 1. Use the cantilever method and determine approximately the reactions at A. All of the columns have the same cross-sectional area. So, we have the figure or the cantilever. So, as you can see, there is a distance to I to H is 20 feet, and the distance in H to G is 22 feet, and the distance in G to F is 17 feet, and the distance in F to C is also 17 feet. And also, we have a force that is 5 kips, and in D is 6 kips. And as you can see, there is a circle, and also known as the moment. So, and as you can see, there is a neutral axis that is in line. So, assumptions. The neutral axis passes the centroid of the cross-sectional areas of the columns. So, number 2, determine the location of neutral axis. So, where is the location is 20 plus A times 42 is equals to 54 times x is equals to 22.67. So in x is equals to 22.67. So we have here so we have to cut the upper part of the cantilever. So here is, so and after cutting we have to cut the we have to cut it, and uh, the 17 feet is cut. So here is 8.5 and 8.5, and there is a neutral axis. So there is a sigma of GF, sigma of HE, and sigma of ID. So sigma of HE over sigma of ID is equals to 2.67 over 22.67 is equals to 0.118 to sigma of HE 0.118 to the sigma of ID. So the value of 2.67 over 22.67 is equals to 0.118. .33 over 22.67 is equals to 0.853. Sigma of GF is equals to 0.853 sigma of ID. So the value of 19.33 over 22.67 is equals to 0.853. So the sigma GF is equals to 0.853. So we come up to 5 kips times 8.5. So we have to solve it for the another value. 0.5, 42.5. So, the answer is sigma of ID is equals to 0.995 kips. So if you're wondering why we come up to this value, is because 42.5 over 42.70, we've come up with this value of 0.995 kips. Wait. Times. So, the value of 5 kips times 8.5 is 42.5. So, that is that. So, the sigma of HE times the area equals to 0.118 times 0.995. In this value is equals to 0.117 kips. So the sigma of GF to the area times the area is equals to 0.853 times 0.995 kips is equals to 0.849 kips. So after that, we have to draw the figure first. So here is the figure. So as you can see, there's a neutral axis and there is the values sigma AD, sigma BE, and sigma CF. And there is force in the cantilever which is 5 kips and in the D area is 6 kips. And the distance of it is 8.5 because we have to cut or to divide in half the 17.17 feet in this area. So the value on I to this is 42.5. Or the value of I to A is 42.5. So let's continue. So sigma of BE over the sigma of AD is equals to 2.67 over 22.67, and the value, and if you solve it, we've come up into 0.118. So sigma of BE is equals to 0.118 sigma of AD, and to the sigma of CF over the sigma of AD is equals to the 19.33 over 22.67 is equals to 0.853. So the value of the sigma CF is equals to 0.853 sigma of AD. So let's continue. So the sigma of AD times to the area times to the 22.67 plus 0.118 sigma of AD times the area of column times to 2.67 plus 0.853 sigma of AD times to the area times 19.33 is equals to 5 kips times 42.5 plus 6 kips times 8.5. So 42.70 times to the sigma of AD times to the area is equals to 2.63.5 kilo feet kips is equals to sigma of AD times to the area. So we've come up in this answer, which is 6.171 kips. So, or we have to divide the 263.5 over to 42.70 so that we also come up to this answer. So let's continue. So, sigma of BE times to the area is equals to 0.118 times to the 6.171 kips. So we've come up to this answer, which is 0.728 kips. So let's continue. So to the sigma of CF times the area is equals to 0.53 times 6.171 kips is equals to 5.264 kips. So let's continue. So in number 4, break the structure at the hinges and draw the free body diagram. So we have to draw the free body diagram. As you can see, there is a free body diagram I drawn, and there is a value of 0.995 kips. .995 in the, which is from the sigma of ID times the area is equals to 0.995 gigs. So in member 2, as you can see, there is a force in 6 skips, and in the LX in the horizontal and the vertical is LY. So there is a JX and J. So in the member 3, in the free body diagram, in the cantilever method, we can see there is a value of 6.171 kips, which is from the this sigma of AD times the area is equals to 6.171 kips. So GX J to the moment A, and there's AX. So 6.171 kips is equals to AY. So we have to solve the member 1. And for member 2, and for number 3, five, 3, 1. And for f of x is 0.531 kips. So as you can see, for member 1, there is kx times to the 8.5 minus 0.995 kips times to the 9 is equals to 0. So we've come up to this answer, which is kx is equals to 0.949 kips. So for member number 2, emission of m to the l is equals to 0. 0.995 kx k I kips times 9 plus 0.949 kips times to the 8.5 plus gx times to the 8.5 minus 6.171 kips times 9 is equals to 0. So the value of gx is equals to 4.531 kips. For the member number 3, summation of MA is equals to 0. So 4.531 kips times 8.5 minus MA. So MA is equals to 338.5 kilofeet. So the summation of forces X is equals to 0. So 4.531 kips minus AX is equals to 0. So we've come up to the answer of AX is equals to 4.531 kips, and for AY is equals to 6.171 kips. So that's it for the example number 1. And also for the example number 2, example number 2. So first we have to draw the figure of the cantilever. So let's continue. So one, add a hinge at the center of each beam, negative 4 degrees. Number 2, add a hinge at the center of each column, negative 6 degrees. At the second floor level, the actual stress in a column is proportional to its distance from the neutral axis, negative 1 degree. The first floor level, the axial stress in a column is proportional to its distance from the NA, or the neutral axis, negative 1 degrees. So the assumption, neutral axis passes the centroid of the cross-sectional areas of the columns. So number 2, determine the location of neutral axis column cross-sectional area is equals to A. So A, so there is the value of x is equals to 18.67. 3. Determine the actual loads in the columns at each floor level according to the overturning moment. So first, we have to draw the figure. So the distance of this is 0.67. So as you can see, you have to cut the 15 feet into 7.5 in the upper corner. So you have the value of 7.5 meters. So if you're wondering why we've come up to this value of 0.67, it's because of 18.67 minus 18. And if you're wondering how we've come up to this value, it's because 38 minus 18.67 is equals to 19.33. So the 38 value is from the, we have to add the 18 feet plus 20 feet. So let's continue. So the sigma of HE over the sigma of ID is equals to 0.67 over 18.67 is equals to 0.0359. So the value of sigma HE is equals to 0.0359 sigma of ID. And the sigma of GF over the sigma of ID is equals to 19.33 over 18.67 is equals to 1.035. So the value of sigma of GF is equals to 1.035 to sigma of ID. So the sigma of GF over the sigma of ID is equals to 19.33 over 18.67. So it's equals to 1.035. Sigma of GF is equals to 1.035 sigma of ID. So the value is sigma of IED is equals to times to the area is equals to 0.581 gibbs. So if you're wondering how we've come up to this value is because 22.5 over 38.70. So we have to draw the figure. So let's continue. So if you're wondering why we've come up to this 2.519K is from the 97.5 kilofeet over 38.70. So the value of sigma CF is times the area is equals to 1.035 times 2.519 is equals to 2.607 kips. So in 4, break the structure of at the hinges and draw the free body diagram. So first we have to draw the free body diagram. So for the member number 1, there is the value. For the member number 2, 0.582. And for the member 3, member number summation of fx equals to 0, so 1.628 keeps minus ax is equals to 0. So come up to this answer, which is ax is equals to 1.628 keeps and ay 2.519 keeps. And for the moment, A is equals to 1.628 k keeps times 7.5 minus moment A is equals to 0. So moment A is equals to 12.2 kilofeet. So here is the answer. So let's review. For member number 1, summation of m to the n is equals to 0. So kx times 7.5 minus 0.581k times to the 9 equals to 0. So kx is equals to 0.697 kips. So for the member 2, summation of ml is equals to 0. 0.581k times to the 9 plus 0.697k times to 7.5 plus jx times 7.5 minus 2.519 keeps times 9 is equals to 0. So we've come up to this answer, which is jx is equals to 1.628 keeps. So in the free body diagram, we see that there is a mx and my, and there is a value of 0.581 kips. So we also see that there is a force 4k in the figure, and lx and ly, and there is a value of 2.519 kips, and there's a moment, and there is a moment a and ax and the area, so gx. So that's all. Thank you.